Hello everyone, welcome to another episode of Math-221. So today we're going to go over section 10.5, which is trees, and then 10.6, which is rooted trees. So first let's talk a little bit about why we care about trees. So a tree is a type of graph, but there are lots and lots of different types of graphs that have names. But the reason we're going to learn about trees is because these are extremely important in computer science. So most massive data sets, like for example Google's index of web pages, Amazon's catalog of products, or Facebook's set of profiles, are actually stored as trees. You might think that they store them as lists, but a list is actually a really inefficient way to store data. Trees are much more efficient because they can be searched, sorted, and updated far more quickly than lists. So that's why this is an important topic for computer science. Okay, so let's get into some definitions. So a graph is said to be circuit-free if and only if it has no circuits. So remember that a circuit, that is a closed walk that has no repeated edges. So in a graph that is circuit-free, the only possible closed walk would have to repeat edges. A graph is called a tree if and only if it is circuit-free and connected. A trivial tree is a graph that consists of a single vertex. A graph is called a forest if and only if it is circuit-free and not connected. So I think it makes a little more sense if you look at some of these pictures here. So the two on the left are trees, and you can see that they do not contain any circuits, because if you were to do a closed walk on that tree, walk from one vertex and then go somewhere else and then come back to that vertex, you would have to repeat edges. And then the third one there, that is a forest. It simply consists of two trees. So if you have more than one tree, then that's a forest. It's kind of not the most creative name. And then the final one there, that is not a tree and it's not a forest because it contains a circuit. So for example, oh, is my pen gonna work? This right here would be a circuit. Okay. So let's look at a couple of more definitions. So let T be a tree. If T has only one or two vertices, then each is called a terminal vertex. If T has at least three vertices, then a vertex of degree 1 in T is called a terminal vertex or a leaf. And a vertex of degree greater than 1 in T is called an internal vertex or a branch vertex. So this is not as complicated as the definition is making it sound. The leaves are just the ones that stick out of the ends of the tree like this. So those all have degree 1. Okay, and then the branches are the ones that are inside of the tree, so they have degree 2 or more. So these are the branches right here. Okay, so let's look at an example. Find all terminal vertices and all internal vertices for the following trees. So the terminal vertices, or the leaves, so I'm doing part B as the example here. These are going to be V1, V2, V5, V6, and V8. And then the internal vertices, or the branches, those are going to be the ones that have degree 2 or more, so those will be V3, V4, and V7. Okay, so this problem right here, that is your homework. So go ahead and do part A and check your answer in the back of the book. All right, now let's look at a couple of theorems for trees. So theorem 10.5.2 says, for any positive integer n, any tree with n vertices has n minus 1 edges. And then theorem 10.5.4 is the converse of that. For any positive integer n, if G is a connected graph with n vertices and n minus 1 edges, then G is a tree. So I'm not going to prove either of these. There are some proofs of them that are in the textbook if you're interested, but I'll just kind of give you the basic idea of why these are true. So to draw a tree, you can do it like this. You can start with one vertex. So I'll just start with that one right there. And then to add more vertices, you need one edge for each extra vertex. and you can't use more than one because then you would create a circuit. Okay, so if I'm going to add one, oops, that's not a good arrow. If I'm going to add more vertices, then I need to add them each with one extra edge connecting back to the original, tree. So if you think about that for a while, I hope this theorem will make sense to you. Okay. Maybe I should like color code this. I don't know. Let me try doing it like that. It might make more sense. So when I'm adding extra vertices, oh, my pen is messing up. I need one edge to attach each extra vertex. Like that. Okay, I'll leave it like that. Okay, so let's look at some more examples. So in these, we're going to either draw a graph with the given specifications, or we'll explain why no such graph exists. So number 15, I'll start there. The graph is circuit-free. It has 7 vertices and 4 edges. So let me make a little, oops, I don't know why my pen is messing up. Okay, so I'll just make this into thirds here. All right, so for 15, circuit-free, 7 vertices, 4 edges. Okay, so I'm just going to draw my 7 vertices in a little circle. And then I need to add 4 edges here without making a circuit, so it's not very hard to do. I can just do them like this. Okay. And then for 16, tree, 12 vertices, and 15 edges. Okay, so we just learned that a tree with n vertices has to have n-1 edges, so this is not going to work. So let me just write the explanation. This is impossible. A tree with 12 vertices would have 11 edges. Okay, and then for 17, we're going to draw a graph with 6 vertices and 5 edges that is not a tree. So remember that we just saw the theorem that said that if the graph is connected and it has n vertices and n-1 edges, then it's a tree. So in order to do this, we're going to need to make it be not connected, otherwise it'll turn into a tree. So I'll just put one there, and then maybe one here, and 2, 4, and then I have to put the 5th one somewhere, but I can't make it a tree, so I'll just make it like that. So that is not a tree because it has a circuit, and also it's not connected, and it has 6 vertices and 5 edges. Okay, so let's look at a couple of more of these, and then I'll give you the homeworks. So for 18, a tree with 5 vertices and total degree 10. Okay, so this might look possible, but it's actually not possible because of something that we learned in the last lesson on Friday. So the total degree, or maybe it was on Wednesday, I don't remember, of a graph is twice the number of edges. So this graph would have 5 edges, but a tree with 5 vertices has 4 edges, something we just learned, so this is impossible. Okay, now let's look at number 19. So we need a graph connected with 10 vertices and 9 edges, and it has a non-trivial circuit. So this is also going to be impossible because of a theorem that we just went over. Okay, I don't remember which one it was, but one of the theorems we just saw said a connected graph with n vertices and n-1 edges is a tree. So this cannot have a circuit because trees don't have circuits. Okay, hope that makes sense to you. All right, so here's some homework problems for you to do, and you can check your answers in the back of the book when you're done with these. All right, so now let's move on to section 10.6. So we're just ripping right through this lesson, which is rooted trees. So I talked before about how trees are really important in computer science, and the types of trees that you do in computer science are usually rooted trees. So a rooted tree is a tree in which there is one vertex that is distinguished from the others, and that is called the root. So in this example graph down here, the root is that one that is at the top. We usually draw them at the top, and then the other vertices are going to be below them. Okay, the level of a vertex is the number of edges along the unique path between it and the root. So you can see here the levels are all labeled here. So like this vertex right here, this is level 4 because it takes 1, 2, 3, 4 edges for it to get back up to the root. So that is level 4. The height of a rooted tree is the maximum level of any vertex in the tree. So if we look at the height, it's measuring like like you would measure it with like a ruler. So the height there is 4, because this is 4 edges high basically. Okay, and then given the root or any internal vertex v of the rooted tree, the children of v are all those vertices that are adjacent to v and are one level farther away from the root than v. So for example, in this graph right here, if we look at u, the children of u are v and w. Another example, this vertex right here, its child is this other vertex that is right below it there. So it has to be adjacent and one level down. So it's kind of like modeled after a family tree. This is the way you would draw a family tree. Okay, and then let's keep looking through these definitions here. If w is a child of v, then v is called the parent of w. Again, that's the analogy to the family tree. And the two distinct vertices that are both children of the same parent are called siblings. Again, think of it as a family tree. Given two distinct vertices v and w, if v lies on the unique path between w and the root, then v is an ancestor of w, and w is a descendant of v. So again, this is all just in complete analogy to the way a family tree works. So for example, all of these vertices that are in that circled region right there, those are all descendants of u, which is right here. So if u was like their grandmother or something, or their great-grandmother. And then of course the root is an ancestor of everything in the entire tree, and everything is a descendant of the root. Okay, so I hope those terms make sense to you. Let's look at some examples. Okay, so here is an example for us to look at. So the root in this tree is v0 right here at the top. What is the level of v8? So if we look at v8, we have to go 1, 2, 3 edges to get up to the root. So that is going to be level 3. Okay, and then what is the level of v0? So v0 is already at the root, so we don't have to travel to the root. So that's going to be level 0. What is the height of this rooted tree? So if we count the maximum, well, maybe I can just like label these levels here. So this is level 0, this is level 1, this is level 2, oops, this is level 3, this is level 4, and then this is level 5. Okay, so the height of this tree is 5. And that's also the maximum number of edges that you have to travel from any leaf to get back up to the root. What are the children of V10? So V10 is right here, and then its children are these ones that are right below it. So that's going to be V14, V15, and V16. What is the parent of V5? So V5 is here, so then its parent is going to be V1. What are the siblings of V1? So the only sibling of V1 is the one that has the same parent as V1. So the parent of V1 is V0, and then V0's other child is V2. Okay, what are the descendants of V12? So V12 is here, so its descendants are going to be all the ones that are below it. So that's going to be V17, V18, and then V19. Okay, I hope that made sense to you. All right, so here is a homework problem for you to try. Go ahead and try these questions and then check your answers in the back of the book. All right, now let's talk about binary trees. So again, this is an important concept for applications in computer science. Many datasets are stored as binary trees. So a binary tree is a rooted tree in which every parent has at most 2 children. So that's the important part right there, at most 2 children. Each child in a binary tree is designated either a left child or a right child, but not both. And every parent has at most 1 left child and 1 right child. A full binary tree is one in which each parent has exactly 2 children. Given any parent V in a binary tree T, if V has a left child, then the left subtree of V is the binary tree whose root is the left child of V. Okay, so like for example, if we look at this graph right here, here's W, and then the left subtree of W would be all of this stuff that I've circled here. And then the right subtree of W would be all this stuff here that I've circled. So if you were to like pinch that off and make a new tree, like cut it off and make a new tree, those are the subtrees. Okay, so let's look at an example here. Okay, so let's look at these. So I'm going to start with number 12. So a full binary tree, 8 internal vertices and 7 terminal vertices. Okay, so let's give a try at doing this. So let's see, there's 3, and then, okay, so now I have 3 internal and 4 terminal. So that's not going to be enough. Let's see if I can keep going. All right, so if I do, this is a little tricky. Okay, I think I've maybe done it. Let me try to count. Oh, no, not quite. I'm gonna have to erase that one. Okay, so here I have 1, 2, 3, 4, 5, 6, 7, 8 internal vertices, and then 1, 2, 3, 4, 5, 6, 7 terminal vertices. So yeah, okay, I think I did it. That was a little bit tricky, but okay. And then 13, binary tree, height 4, 8 terminal vertices. Okay, so let's see if we can do, actually, 1, 2, 3, 4. I think if I just do the same one as the last one, but put 1 extra terminal vertex on, I think that will do it. Okay, so that's height 1, and then this is height 2, and then that is height 3. Okay, so that'll be height 4. And then let me keep going a little bit to put more terminal vertices. Okay, so I think that has 8 terminal vertices and it has height 4. Okay, so here are some homework problems for you to try. So go ahead and do these and check your answers in the back of the book. All right, that's it for today, everybody. It's a really short lesson, so hopefully you enjoyed that, and I'll see you next time.